Somewhere in the metal fixtures around you, quietly, without asking permission or announcing itself in any way, a great many impossibly small regions are settling into alignment. In the steel of a door frame, in the thin wire coiled inside a lamp, in the tiny clasp holding a necklace shut in a jewelry box across the room, there are patches so small you could fit millions of them across the width of a single eyelash, and each one behaves like its own miniature compass. Some of these patches point one way, some point another. Right now, most of them are not agreeing with each other at all, which is why the doorframe is not tugging at your attention and the lamp wire is not humming with any noticeable pull. But the capacity is there, sitting quietly inside the ordinary objects of the room, waiting. This is a strange thing to sit with. If you let yourself really sit with it, you are surrounded, most likely, by materials that could organize themselves into something that reaches across empty space and moves other objects without touching them, not because someone built a machine to do this, not because there's a hidden battery or a hose or a string, just because of how the atoms happen to be arranged, and for most of human history, nobody could explain why. Let's slow down and think about what a magnet actually does, because it's easy to let the familiarity of the thing paper over how genuinely odd it is. Picture a small, dark stone, cool to the touch, sitting on a wooden table. Nothing about its surface looks different from any other rock you might pick up on a walk. It doesn't vibrate. It doesn't glow. If you set it down next to a pile of iron filings, though, something happens that no amount of staring at the stone's surface would have predicted. The filings rise, not all at once in a dramatic leap, but in a kind of eager creeping, as if the metal itself has decided it wants to be closer to the stone, filament by filament, gathering into little bristled clumps around two particular regions of it. Nothing touched the filings first. No breeze moved them. No warmth radiated out to explain it away as some trick of heat and air currents. And yet, across a small gap of ordinary space, ordinary emptiness, something reached out and moved them. People noticed this a very long time ago, long before there was any framework for describing what was happening. There are accounts, hazy with retelling but persistent across cultures, of shepherds in the ancient world, noticing that the iron nails in their sandals seemed to stick to certain black stones scattered on hillsides near a region called Magnesia in what is now western Turkey. Whether that particular story happened exactly as it's told or not, we know that stones like this, later called lodestones, turn up in the historical record across many separate civilizations, each one arriving independently at the same startled observation. In ancient China, by at least the 3rd century before the Common Era, texts describe a spoon-shaped lodestone that would swing and settle in a particular direction when placed on a smooth surface, a device sometimes called a south pointer, used first in divination and only later adapted for the more practical business of finding your way across land or sea. The Greeks wrote about the same stones with a mixture of fascination and unease, and Aristotle mentions that Thales of Miletus, one of the earliest thinkers we have record of, was struck enough by the pulling behavior of these stones that he wondered whether they might be alive in some sense, whether the pull was a kind of desire, an early guess at something the stone did because it wanted to. That's worth pausing on for a moment, because it tells you something about how deeply strange this force felt to the people who first tried to explain it. When something moves without visible contact, without wind, without any thread connecting it to the thing that moved it, the most natural explanation available to someone in the ancient world was that maybe it moved because it wanted to. Life was the only category anyone had for spontaneous, unexplained motion. It would be well over 2,000 years before anyone had a better category to put it in, and even then, the better category didn't so much explain magnetism away as give it a much larger and much stranger home. Consider your own hands for a moment, resting wherever they happen to be right now, maybe on a blanket, maybe folded against your chest. If you were to hold two ordinary magnets, the kind that might be stuck to a refrigerator door, and bring them close together with the right sides facing each other, you would feel something that has no real equivalent anywhere else in your daily physical experience. Not the resistance of pushing two solid objects together, not the smooth glide of one surface sliding past another. Something more like an invisible cushion of taut air building between your palms, a spring that seems to exist in the empty space itself, growing firmer as you push the magnets closer until your muscles are straining against something that, if you looked at the gap between your hands, appears to contain absolutely nothing at all. Flip one of the magnets around, and the entire feeling reverses. Now, instead of resistance, there's an eager tug, an urge in your hands to let the two objects leap together and click, sometimes hard enough to pinch skin if you're not paying attention. Same two objects, same distance apart. Only the orientation changed, and the invisible relationship between them flipped from a shove to an embrace. If you have young children, or if you remember being one yourself, you might recall that this simple flip is often the very first, genuinely mysterious thing a person encounters in the physical world. Not mysterious in the sense of not yet having been taught the answer, the way you might not yet know the capital of a country, but mysterious in the deeper sense that something invisible is clearly, undeniably doing work in the space between two objects, and no one around you can fully point to what that something actually is, not in a way that satisfies the way you can point to a rope, or a hand, or a gust of wind. And this is really the heart of what makes magnetism such a strange corner of the physical world to think about, gently, as you settle further into rest tonight. Most of the forces we grow up learning to trust are forces of contact. You push a door, and the door moves because your hand is touching it, transferring motion the way one leaning row of dominoes transfers motion to the next, unbroken. You pull a wagon, and the wagon moves because the rope is taut between your fist and the wagon's handle, an unbroken chain of pulling all the way down. Even a whispered voice reaching someone's ear across a room is, at the deepest level, a chain of touching, air molecules bumping into their neighbors in a long relay, one nudging the next, all the way to the eardrum. But a magnet doesn't need any of that. It reaches across a gap of true nothing. No rope, no relay of touching molecules, no visible mediator of any kind, and it still manages to organize the behavior of another object on the far side of that gap. For most of recorded history, this simply had no explanation that fit comfortably inside the other explanations people already trusted, which is part of why lodestones ended up treated as things closer to charms or omens for so long, kept in cabinets of curiosities alongside unicorn horns and strange fossils, admired and used, but not understood in any way that connected them to the rest of how the physical world seemed to work. It would take many centuries and a slow chain of careful, sometimes accidental observations before anyone began to suspect that this quiet stone-pulling nail phenomenon might be woven into something enormous, something connected to electricity, to light itself, to the very way your eyes are managing to register the shape of a room around you right now, if they happen to be open. But that connection is still ahead of us in this telling. For now, it's enough to simply let the mystery sit there, unresolved and a little wondrous, the way it must have sat with a shepherd on a rocky hillside near Magnesia, feeling the tug of ordinary sandal nails toward the ground, with no word yet in his language for what he was feeling happen in his own two hands. Let's stay with that mystery a little longer, but let's turn it over now, gently, and look at its shape. Every magnet you will ever hold, from the small gray disc stuck to a refrigerator to the great humming rings inside an old television set, has two ends, and those two ends are not the same as each other. People call them poles, and they called them north and south long before anyone knew why those names made sense, simply because a magnet, if you let it hang freely from a thread or float on a sliver of wood in a bowl of water, will turn on its own and settle with one end pointing roughly toward the north and the other pointing roughly toward the south. It does this quietly, without being asked, the way a sleeping cat will turn over in a patch of sun without waking. Sailors noticed this behavior long before physicists had any account of it, and they built their compasses on nothing more than that reliable turning, trusting a stone's habit of pointing without ever needing to know what it was pointing at or why. Here is the first strange and useful fact to let settle into you. If you take two magnets and bring their like poles together, north near north or south near south, you will feel a soft, stubborn resistance, as though the space between them has grown slightly thick, slightly reluctant, pushing back against your hand the closer you try to bring them. But turn one of the magnets around so that north faces south, and that resistance disappears entirely, replaced by something closer to eagerness, a gentle snap as the gap closes and the two pieces come together with a small, definite click. Opposite poles pull toward each other, like poles push apart. It is such a simple rule that it barely feels like it deserves to be called a law of nature, and yet it governs the trembling needle of every compass, the low hum of every electric motor, and the invisible shield around this entire planet that keeps the raw wind of the sun from stripping away the air you are breathing right now. It helps, at this point in the night, to imagine holding one of these magnets in your two hands, turning it over slowly, feeling for some kind of seam or dividing line where the north end stops being north and the south end begins. You will not find one. There is no ridge, no change in texture, no faint border drawn anywhere on the metal. The distinction between the two poles is not a property of the surface, the way a coin has a head side and a tails side stamped into it by a die. It is something deeper, something that seems to belong to the entire object all at once, from one end to the other, as though the whole bar of metal has quietly agreed, atom by atom, to face the same direction. And this is where the story gets a little more delicate and a little more interesting, so let your mind soften around it, rather than gripping too tightly, the way you might hold a moth without wanting to bruise its wings. Long ago, when people first began to draw pictures of how a magnet's influence spread out into the space around it, they used curved lines looping from one pole to the other, arching up and over like the meridians on a globe, or like the grooves you can trace with your fingertip on a seashell. If you have ever scattered iron filings on a sheet of paper laid over a magnet,
You may have seen these lines appear almost by magic, the tiny iron flecks snapping into curved rows that seem to trace an invisible structure hiding underneath the paper the whole time, patient and waiting to be revealed. It is a beautiful thing to watch, and it is easy, watching it, to start believing that these lines are real objects, delicate invisible threads strung permanently through space, the way threads might be strung permanently between two nails on a wall. But that isn't quite what they are, and letting go of that particular image, gently, is part of building a truer and calmer picture of what a magnetic field actually is. The lines are a kind of map, not a kind of thread. They are a way of drawing, at every point in space, which direction a small compass needle would point if you placed it exactly there, and how strongly it would feel pulled to turn that way. Where the lines bunch close together, the pull is strong. Where they spread apart and thin out, the pull grows faint, fading the way the warmth of a fire fades the farther back you sit from it in a dim room. The iron filings do not reveal threads that were secretly there all along. Each little sliver of iron becomes, for a moment, a tiny magnet itself, and lines up the same way a whole compass needle would. And the pattern they form together is simply many small answers to the same question, asked over and over, at slightly different points, stitched into one continuous-looking picture by your eye. The lines are a beautifully useful way of thinking, a tool for drawing what is otherwise invisible, but nobody has ever found an actual thread out there in the empty air, no matter how closely they've looked. Now let the mind wander toward a question that feels almost embarrassingly simple, the kind of question a very young child might ask, while turning a refrigerator magnet over and over in small fingers, before anyone has taught them not to ask it quite so plainly. If a magnet has a north end and a south end, what happens if you cut it in half? Surely, you might think, lying there letting the idea drift, you would end up with one small piece that is purely north, holding only a north pole, and another separate piece that is purely south, holding only a south pole, two tidy halves of the original whole, each pure and single in what it is. It would be a very neat and satisfying answer. It is also not what happens, not even a little. If you were to cleanly cut a bar magnet in half, right through its middle, you would not get an isolated north piece and an isolated south piece. You would instead get two smaller magnets, each one complete, each one carrying its very own north pole and its very own south pole, as though the object had simply reproduced its own wholeness at a smaller size, rather than splitting its identity in two. Cut one of those smaller pieces in half again, and the same thing happens once more, smaller still, but whole again, north and south together, refusing to be pulled apart into pure, single ingredients.
As far as anyone has ever been able to observe, in any laboratory, with any material, using any method of cutting, grinding, melting, or breaking, this pattern holds without exception. Every fragment, no matter how small, insists on having both a north end and a south end of its very own. Physicists have gone looking, seriously and carefully, for what they call a magnetic monopole, a single isolated north with no south anywhere attached to it, or a single isolated south with no north, some fundamental particle that would be pure one thing and nothing of the other. Certain elegant theories about the deep structure of the universe even predict that such a thing ought to exist somewhere, in principle, under the right conditions. But in all the ordinary matter that makes up this room, this bed, these hands, no one has ever actually found one, not once, not anywhere, and the search for that lonely single pole remains open, unresolved, sitting quietly at the edge of what is known. So the poles seem to come as an inseparable pair, again and again, at every scale anyone has managed to check, bound together the way the two sides of a single coin are bound together, in the sense that you could never peel just one side away and leave the coin still a coin. And this insistence on always coming in twos, on every fragment carrying its own complete little compass within it, turns out to be an early clue, a small breadcrumb left along the path, pointing toward the deeper and stranger truth about where magnetism actually comes from in the first place. Because it does not come from some magical dust sprinkled only into certain rare rocks pulled from a hillside near Magnesia. It comes, as it turns out, from something in motion, something happening quietly inside every single atom of every single piece of matter around you, whether that matter shows any sign of being magnetic or not. Let's slow down for a moment and just sit with an old rock. Somewhere in antiquity, probably more than 2,000 years ago, in a region of Greece called Magnesia, herders and travelers noticed something strange about certain dark stones scattered in the hills. Iron tools would catch on them, a knife set down too close would tug, ever so slightly, toward the stone, as if the stone wanted it. Nobody understood why. Nobody had any framework for understanding why. There was no concept of a field, no concept of force acting invisibly across empty space. There was only the stone and the strange, undeniable fact that it pulled at iron the way nothing else in the world seemed to pull at anything. They called this material lodestone, and for a very long time, that was simply what it was, a curiosity, a piece of folklore, something a merchant might keep in a drawer to show visitors. But somewhere along the way, someone made a discovery that mattered far more than the pulling itself. Someone noticed that if you took a sliver of lodestone or a piece of iron that had touched it and let it float freely on a piece of wood in a bowl of water, say, or hung from a thread so it could turn without friction, it did not just sit there. It turned. It swung around on its own, slowly, gently, until it settled into a particular direction, and it did this every single time, no matter how many times you nudged it away and let it go again. That direction, it turned out, was roughly north and south. And once people noticed this, once they understood that a piece of lodestone always wanted to point the same way, everything changed for anyone who had ever needed to find their way across open water or open desert with no landmarks in sight. This was the birth of the compass, and it appeared, independently and at different times, in China, in the Islamic world, in Europe, each culture arriving at the same simple, quiet magic, a stone that always knows which way is north. Sailors, who had once hugged coastlines, afraid to lose sight of land, could now venture out into open ocean with something to trust when the stars were hidden by cloud. But here is the interesting part, the part worth sitting with for a while. For centuries, nobody actually knew why the compass pointed north. They simply knew that it did. They used it. They built entire systems of navigation and trade around it. But the explanation, the actual reason the needle turned that way, remained a mystery wrapped inside a very useful tool. Some thought there was a great magnetic mountain somewhere in the far north, pulling every compass toward it like an enormous, invisible lodestone. Others imagined the pole star itself exerted some kind of pull. The truth, as it turned out, was stranger and closer to home
than either of those guesses. It took until the year 1600, in England, for someone to work out what was really happening, and that someone was a physician named William Gilbert. Gilbert served as a doctor to Queen Elizabeth I, but his real passion, the thing he poured his private hours into, was magnetism. And he did something that seems almost obvious now, but was genuinely radical at the time. He experimented. Carefully, patiently, methodically, rather than simply speculating from an armchair, the way so many before him had done. Gilbert carved a large sphere out of lodestone, a kind of miniature globe, and he called it a torella, a little earth. Then he took a small compass needle and walked it around the surface of this stone globe, watching how it behaved at different points, near the poles of the sphere, near its equator, tilted this way and that. And what he found was remarkable. The little needle behaved, in miniature, exactly the way compass needles behaved on the actual surface of the actual Earth. Near the poles of his little stone globe, the needle dipped sharply downward, just as real compass needles were known to dip near the Earth's magnetic poles. Near the equator of his globe, the needle lay flat, just as it did near the Earth's actual equator. From this, Gilbert drew a conclusion that must have felt almost dizzying at the time. The Earth itself, he proposed, the whole planet beneath everyone's feet, was itself one enormous magnet, not pulled by some distant magnetic mountain, not tugged by a star, but generating its own magnetism from somewhere deep within its own body. He published this idea in 1600 in a book called, in Latin, roughly translated, On the Magnet, and it is often considered one of the first true works of experimental physical science, because Gilbert insisted on testing his ideas against careful observation rather than simply reasoning about how the world ought to behave. And yet, even with this beautiful insight, Gilbert still had no idea why the Earth was magnetic, and no idea that magnetism might be connected to anything else in the world at all. For him, and for nearly everyone who came after him for the next 2 centuries, magnetism and electricity were entirely separate subjects. Electricity was the crackle of static on amber rubbed with cloth, the strange spark you could draw from a charged glass rod. Magnetism was the pull of lodestone and the swing of a compass needle. 2 different phenomena, studied by different people, appearing in different textbooks, with nothing obvious connecting them. That separation held, quietly, for generation after generation, until the year 1820, when a Danish physicist named Hans Christian Ørsted was giving a lecture, demonstrating some simple experiments with electric current for a small audience of students. And almost by accident, while a wire carrying current happened to lie near a compass on the table, he noticed the compass needle twitch. Not because anyone touched it, not because of any wind or vibration in the room. It moved because current was flowing through the nearby wire, and somehow, that flow of electricity was nudging the needle, the way a hand might.
It is worth pausing on how strange this must have felt in the moment. 2 subjects that had lived in entirely separate rooms of human understanding for over 2,000 years, electricity and magnetism, storms and stones, suddenly reached across the table and touched each other. Ørsted did not fully understand what he was seeing, not right away, but he had the sense to keep testing it, to move the wire, reverse the current, watch the needle respond each time in a way that was clearly not coincidence. News of this discovery spread quickly across Europe, and it reached a French physicist named André-Marie Ampère, who took Ørsted's simple, almost accidental observation and turned it into careful, rigorous science. Within just a few weeks of hearing about Ørsted's result, Ampere had worked out mathematical relationships describing how electric currents create magnetic effects, and how two wires carrying current can push or pull on each other from a distance without ever touching, simply because of the currents flowing within them. Electricity in motion, it was becoming clear, could produce magnetism. The two were not separate rooms after all. They were connected passageways in the same house, and people were only now discovering the doors between them. If moving electricity could create magnetism, a young English scientist named Michael Faraday began to wonder, working in London a few years later, could the reverse also be true? Could magnetism, under the right conditions, create electricity? Faraday had almost no formal mathematical training, having come from a poor family and worked as a bookbinder's apprentice as a boy, teaching himself science by reading the very books he was binding. But he had an extraordinary gift for careful, patient experiment and an intuitive feel for what might be happening in the invisible space around wires and magnets. Faraday discovered that if you moved a magnet near a coil of wire, or moved a coil of wire near a magnet, a current would appear in that wire, but only while something was moving. A magnet sitting perfectly still next to a coil produced nothing at all. It was the motion, the changing, that seemed to matter, and this discovery, quiet as it seemed in his notebook, would eventually make it possible to generate electricity on an enormous scale in every power station humming somewhere in the world tonight. Let's leave Faraday's coils and wires for a while and travel down into something smaller and quieter. Let's travel into the iron itself, because there is a question we have been circling without quite landing on, and it is a good one to rest with. What is actually happening inside a piece of iron that lets it become magnetic in the first place? Not the wire wrapped around it, not the current flowing through the coil, but the metal itself, sitting there, gray and solid and ordinary looking, on a table in a workshop or in the frame of a door hinge. Why does iron respond to magnetism so eagerly when most other materials, most wood and glass and copper and stone, barely seem to notice a magnet's presence at all? The answer begins, as so much of this story does, with something almost too small to imagine, and yet it is the only place the answer can begin. It begins with the electrons. You may remember, from earlier in this long night, that every electron behaves, in its own strange quantum way, like an impossibly tiny magnet. It has what physicists call a magnetic moment, a kind of built-in north and south, arising from a property called spin, which is not really spinning in the way a top spins, but which produces effects as if it were. Every electron in every atom, in every material in the universe, carries this tiny magnetic quality with it, everywhere it goes. This is true of the electrons in a block of wood, just as much as it is true of the electrons in a bar of iron. So the difference between magnetic materials and non-magnetic ones cannot simply be that one has these tiny magnetic electrons and the other does not. They all have them. The difference must lie somewhere else, and it does. It lies in what those tiny magnets are doing, moment to moment, in relation to one another. Picture, if you can, an enormous auditorium filled with people, and imagine that every single person in that auditorium is holding a small compass needle out in front of them, free to point in whatever direction they like. In most materials, if you could look down at all those needles from above, you would see them pointing every which way, no organization at all, a scatter of arrows in every possible direction, canceling each other out almost perfectly when you average them all together. One needle points north, its neighbor points nearly south, another points east, and by the time you have added up the whole auditorium, the net effect is close to nothing. This is why most substances show only the faintest, almost undetectable magnetic response, and why you can wave a magnet near a coffee mug or a wooden spoon and feel nothing happening at all. But in iron, and in a small handful of other elements, cobalt and nickel being the other two most familiar ones, something different happens. Something in the deep quantum mechanical structure of these atoms encourages neighboring electrons to align their tiny magnetic moments with each other rather than pointing randomly. It is a subtle effect, tied up in how electrons interact with their close neighbors, according to rules that even now are not completely settled in every detail among physicists who study the fine points of solid-state matter. But the broad picture is well understood, and it is this. In materials like iron, nearby atoms tend to encourage each other's electron spins to line up in the same direction, the way a small group of people standing close together in a crowd might start walking in step without ever discussing it, simply responding to the rhythm of the people beside them. Now, if this alignment happened uniformly across an entire piece of iron, every single atom pointing the same way from one edge of the metal to the other, then every piece of iron in the world would already be a powerful magnet all the time, without any effort required. But that is not what we observe. Most iron, most of the time, is not strongly magnetic on its own. A nail does not usually pick up paper clips just sitting on a table. So there must be something more to the story, some further layer of organization or disorganization that explains why raw iron behaves so differently from the magnets we buy or make. This is where the idea of magnetic domains comes in, and it is one of the more beautiful hidden structures in ordinary matter, invisible to the eye, but real all the same. Inside a piece of iron, the alignment of electron spins does happen, but it happens in patches, in neighborhoods, rather than across the whole material at once. Physicists call these patches domains. Within any single domain, which might be a region only a fraction of a millimeter across, or sometimes larger, all the atomic magnetic moments are indeed lined up together, cooperating fully, pointing in one consistent direction, exactly as our imagined crowd of people walking in step. But the iron as a whole is made up of an enormous number of these domains, and crucially, different domains tend to point in different directions from one another. One neighborhood of atoms might have its collective compass needle pointing to the left. The neighborhood right beside it might point downward, or diagonally, or in the opposite direction entirely. And when you add up the magnetic effect of all these domains together, pointing every which way, like the scattered needles in our auditorium, but now scattered domain by domain, instead of atom by atom, the overall magnetism of the iron often cancels out to something quite small. This is why an ordinary iron nail, despite being made of a material that is inherently capable of strong magnetism at the atomic level, does not usually behave like a strong magnet itself. Its potential is there, humming quietly within each domain, but that potential is scattered in competing directions and mostly cancels out when you step back and look at the whole. So what changes this? What turns an ordinary,
magnetically neutral piece of iron into something that will hold papers to a refrigerator door for years? The answer has to do with encouraging those domains to agree with each other, to stop pointing every which way, and instead point largely in the same direction. And there are a few ways this can happen, some gentle, and some more forceful. One way is to place the iron inside a strong external magnetic field, the kind produced by a coil of wire carrying current, echoing back to Ørsted's discovery. When a magnetic field is applied from outside, it exerts a gentle pressure on every domain within the iron, nudging the boundaries between domains to shift. Domains that happen to already be aligned with the external field tend to grow larger, expanding at the expense of their neighbors, while domains pointing in less favorable directions shrink. It is a bit like a town meeting, where one opinion is being gently, persistently reinforced by an outside voice, and over time, more and more of the town starts to lean that way, not because anyone was forced, exactly, but because the pressure kept nudging things in one direction. If the external field is strong enough, and applied long enough, nearly all the domains can end up aligned in roughly the same direction, and at that point, the iron as a whole becomes strongly magnetized, its scattered neighborhoods now marching together. Remarkably, in certain kinds of iron and steel, once this alignment has been achieved, it can persist even after the external magnetic field is removed. The domains, having been coaxed into cooperation, tend to stay that way, at least for a while, sometimes for a very long time, held in place by the internal structure of the metal itself, by tiny imperfections and boundaries within the crystal that make it energetically costly for the domains to slip back into disorder. This is what we mean by a permanent magnet, though permanent is always a matter of degree and circumstance rather than an absolute guarantee, as we will see. Because there are ways to undo this alignment too, and they tend to involve either heat or violence, in a gentle physical sense. Heat is the more elegant disruptor. As you warm a magnetized piece of iron, the atoms and their surrounding electron clouds gain more thermal energy, more restless jostling and vibration, and this jostling makes it harder for neighboring magnetic moments to stay obediently aligned with one another. Think of our crowd of people walking in step again, and now imagine the room getting hotter and more chaotic, everyone growing more agitated and distracted, until the neat marching rhythm starts to break down into disorganized shuffling. At a certain specific temperature, different for each magnetic material, and named the Curie temperature after Pierre Curie, who studied this effect carefully in the 1890s, the alignment collapses entirely. For iron, this temperature is around 770 degrees Celsius, hot enough to glow, and above it, iron loses its capacity for this kind of ordered magnetism altogether, its domains dissolving into randomness, only to potentially reorganize again as the metal cools back down, if a field is present to guide them.
Mechanical disturbance can have a similar unraveling effect, though through a rougher mechanism. Striking a magnet sharply with a hammer, or dropping it repeatedly onto a hard floor, can jolt the crystal structure of the metal, disturbing the boundaries between domains and allowing them to slip back toward a more disordered, less cooperative arrangement, weakening the magnet's overall strength. Sailors on old wooden ships, long before anyone understood domains or Curie temperatures in any formal sense, already knew from hard experience that a compass needle could lose its reliability after rough handling and would sometimes need to be remagnetized by stroking it against a known strong magnet to restore its wandering, straying atoms to some semblance of order once more. So let's leave the hammer and the hot iron for a moment and follow a different thread entirely, one that seems at first to have nothing to do with magnets at all. Let's follow a current of electricity through a plain copper wire. For a long time, electricity and magnetism were treated as entirely separate subjects, studied by different people, written about in different books, taught as though they simply happened to share a chapter in the same textbook by coincidence. Static electricity, the kind that makes your hair rise near a balloon, seemed to belong to one tidy family of phenomena. Magnets, with their invisible pulling and pushing, seemed to belong to another. Nobody had any strong reason to think these two families were secretly related, cousins who had simply never been introduced to each other at a party. Then, in 1820, a Danish physicist named Hans Christian Ørsted was preparing a lecture demonstration for his students, and something small and strange happened, something that in hindsight now looks almost too neat to be a genuine accident, though by most accounts it really was one. He had a wire connected to a battery, and nearby, entirely unrelated as far as anyone assumed, sat a compass. As he closed the circuit and current began flowing through the wire, the compass needle, which should have had no reason to care about a piece of copper carrying electricity, twitched. It swung. It settled into a new direction, no longer pointing north, but instead pointing in a direction determined by the wire itself. Picture it slowly, because it deserves to be pictured slowly. A quiet lecture hall, oil lamps or early gas lighting, casting soft shadows, students watching, perhaps a little bored, expecting nothing more than a routine demonstration of current and voltage, and then this small brass needle, this ordinary compass that had spent its whole existence dutifully pointing toward magnetic north, simply stops doing that, and turns instead to face the wire, as though the wire itself had become, however briefly, however faintly, a kind of magnet. Ørsted did not fully understand what he was seeing right away, and to his credit, he did not rush to publish some grand overconfident theory. He spent months quietly repeating the experiment, adjusting the current, moving the compass to different positions around the wire, trying to map out exactly what shape this new invisible influence seemed to take. And what he eventually found was this: the magnetic effect did not simply radiate outward from the wire, the way light spreads from a candle, evenly in all directions. Instead, it curled. It wrapped around the wire in circles, like grooves cut into the surface of a cylinder, endless loops with no beginning and no end, wound around the straight length of the current, the way a spiral staircase winds around its central column. This is worth sitting with, because it is genuinely one of the more elegant shapes in physics, gentle and orderly. If you were to hold a wire carrying current and imagine slicing through the space around it, at any point along its length, the magnetic field would form a perfect circle around that slice, always at right angles to the direction the current is flowing, always closed, always looping back on itself. There is a simple trick for remembering the direction of these loops, sometimes called the right-hand rule, where if you imagine gripping the wire with your right hand, thumb pointing in the direction the current flows, your curled fingers trace the direction the magnetic field circles around it. It is a small physical mnemonic, but it captures something true and structural about the world, not just a memory aid invented for convenience. So a moving charge, a current, produces a magnetic field, not because the wire itself has become magnetic in the way a piece of iron becomes magnetic, with its little domains lining up, but because the moving charges themselves are the source of the field, in a more direct and immediate sense. Stop the current, and the field vanishes instantly,
with none of the lingering, gradual quality of a magnet cooling down from above its Curie temperature. Start the current again, and the field reappears immediately, wrapped in the same tidy circles as before. It is a magnetism made on demand, tied moment to moment to the motion of charge, rather than something baked slowly into the structure of a material. Now, a single straight wire carrying current makes a fairly weak and diffuse field, these loops spreading outward and growing fainter with distance, not terribly useful on their own for most practical purposes. But here is where the story becomes genuinely clever, and where a great deal of the technology surrounding us quietly depends on an idea that is almost embarrassingly simple once you see it. If a straight wire creates a loop of magnetic field around itself, what happens if you bend the wire into a loop of its own? Picture taking that straight wire and curling it around, forming a single ring, a circle of copper with current flowing around its circumference. At every point along this ring, the current is still creating its own small circular field, wrapping around the wire exactly as before. But now, because the wire itself is curved into a loop, all these small individual field circles begin to cooperate rather than scatter randomly. Inside the ring, the fields from every part of the wire point in roughly the same direction, reinforcing one another, adding together, like many small voices humming the same note until the note becomes noticeably louder. Outside the ring, the fields tend to spread apart and cancel more, weaker and messier, but inside, concentrated and aligned, you get something that behaves remarkably like a small bar magnet, with a north-seeking face on one side of the loop and a south-seeking face on the other. And if one loop does this, then what happens with 2 loops, or 10, or 100, wound one after another in a tight spiral, a helix of wire that we now call a coil, or more formally, a solenoid, a word borrowed from Greek roots meaning something like a pipe-shaped channel. Each loop contributes its own share of aligned magnetic field down the center, and because they are wound so closely together, these contributions stack, layer upon layer, the way each additional blanket on a cold night adds a little more warmth, cumulative rather than wasted.
A coil of 100 turns, carrying the same current as that single lonely loop, produces a magnetic field roughly 100 times stronger down its central axis, assuming the turns are wound closely and consistently. This is not some mysterious multiplication trick. It is simply many small, identical contributions added honestly together, the same principle you might use counting how much warmer you feel wrapped in 10 thin blankets instead of 1. This device, a coil of wire carrying current, is what we call an electromagnet, and it has one profoundly useful property that a permanent magnet, made from iron or alnico or some other magnetized alloy, simply does not have. You can turn it off. Cut the current, and the magnetism disappears, cleanly and completely, without any need for heating it above a Curie temperature or striking it with a hammer to disrupt its domains. Restore the current, and the magnetism returns instantly, obedient and controllable in a way that natural magnetism, locked into a chunk of solid iron, never quite manages to be. Now, there is one more piece to this puzzle, one more layer of usefulness that engineers in the 19th century discovered fairly early on, and it circles us back, quite literally, to that hot, glowing iron from a moment ago. If you take a coil of wire and simply wrap it around a core made of soft iron, rather than leaving its center hollow and filled with ordinary air, something remarkable happens
to the strength of the resulting magnetic field. The current, flowing through the coil, creates its modest magnetic field as before, but this field now passes through the iron core sitting inside the coil, and that iron, recall, is itself made of countless tiny magnetic domains ready and willing to align. The field from the coil nudges these domains into cooperation, the same way a compass needle nudges into alignment near any external field, and once aligned, these domains contribute their own magnetism on top of what the coil alone was producing. The iron essentially amplifies the field passing through it, sometimes by a factor of many hundreds, occasionally even thousands, depending on the particular alloy and how it has been treated.
This combination, a coil of wire wound around a soft iron core, connected to a source of current that can be switched on and off at will, became one of the most quietly transformative devices of the industrial age, though it rarely gets much credit for how unglamorous and essential it turned out to be. Let your mind drift now toward a quieter kind of question, one that flips everything you just settled into. If a current can create a magnetic field, wrapping itself around a nail or a coil and coaxing iron into cooperation, does the reverse ever happen? Can a magnetic field, sitting there quietly, somehow create a current? For a long time, nobody knew the answer, and it took a particularly patient Englishman to find it. His name was Michael Faraday, and he did not start out as anyone's idea of a scientist. He was born in 1791 in a poor part of London, the son of a blacksmith, and as a boy he had almost no formal schooling. He was apprenticed instead to a bookbinder, and it was there, stitching together other people's ideas quite literally, page by page, that he began reading the books passing through his hands rather than merely binding them. One of those books happened to be about electricity, and something in it caught hold of him and never quite let go. Through a combination of persistence and lucky timing, he managed to attend a lecture by the great chemist Humphrey Davy, took careful notes, bound them into a small volume, and sent them to Davy as a kind of audition. It worked. Davy eventually hired him as a laboratory assistant, and Faraday spent the following decades in that laboratory, turning himself into one of the most important experimental scientists who ever lived, all without ever mastering the mathematics that later scientists would use to describe his own discoveries. In 1831, working with coils of wire, magnets, and a great deal of quiet trial and error, Faraday noticed something curious. If he held a magnet perfectly still near a coil of wire, nothing happened. No current appeared, no matter how strong the magnet was. But if he moved the magnet, sliding it toward the coil or pulling it away, a current sprang into existence in the wire, however briefly, for exactly as long as the magnet kept moving. The moment the motion stopped, the current vanished again, even with the magnet sitting right there, its field as present and as strong as ever. Stillness produced nothing. Change produced everything. This turned out to be one of the deepest and most useful facts in all of physics, and it goes by the name electromagnetic induction. What matters, Faraday realized, is not how much magnetic field is passing through a loop of wire at any given instant, but whether that amount is changing. Picture the magnetic field passing through the loop as something like sunlight falling through an open window onto the floor of a room. If the amount of sunlight stays constant, nothing dramatic happens to the floor. But if you begin opening and closing the shutters, letting more light in and then less, over and over,
That changing pattern of light and shadow becomes something your eye immediately notices and responds to, even though a perfectly steady beam of the very same sunlight would have gone unremarked. A wire loop is a bit like that eye. It is largely indifferent to steady magnetic fields, however strong. It responds only to change. Physicists came to describe the total amount of magnetic field passing through a loop with a term called flux, a word that literally means flow, though nothing is actually flowing through the loop in any material sense. Flux is simply a way of counting how many of those invisible field lines, the ones a compass needle traces out around a magnet, happen to be threading through the area the loop encloses.
And Faraday's law, which he demonstrated experimentally decades before anyone wrote it down as a tidy equation, says essentially this: whenever the flux through a loop of wire changes, a voltage appears around that loop, and if the loop is part of a closed circuit, a current will flow. Move the magnet closer, and the flux increases, and a voltage appears. Pull the magnet away, and the flux decreases, and a voltage appears again, though in the opposite sense. Wiggle the magnet back and forth, and the voltage wiggles back and forth along with it. It did not matter, Faraday found, whether it was the magnet that moved or the coil of wire that moved instead, sliding away from a stationary magnet. All that mattered was the relative motion between them, the constant reshuffling of how much field passed through the loop from one moment to the next. There is a wonderful, almost mischievous little rule that governs the direction this induced current chooses to flow, and it was worked out a few years after Faraday by a Russian physicist named Heinrich Lenz. Lenz's law states that the current induced in a loop will always flow in whatever direction opposes the very change that created it. This sounds almost too tidy to be true, as though the universe has developed a small stubborn streak, but it follows directly from a much older and stricter principle, the conservation of energy. Think about what it would mean if it worked the other way, if the induced current instead cooperated with the change that produced it, reinforcing rather than resisting. Push a magnet toward a coil, and if the resulting current helped pull the magnet in faster, you would get more motion for free, which would produce more current, which would produce more motion, and so on, spiraling upward into a machine that generates limitless energy from nothing at all. Nature, as far as anyone has ever been able to tell, does not allow this. So instead, the induced current always pushes back. Shove a magnet toward a coil, and the current that springs up arranges itself to create a magnetic field of its own that repels the incoming magnet, resisting your effort to push it closer. Pull the magnet away, and the induced current flips its arrangement to attract the retreating magnet instead, resisting your effort to pull it away. Either way, you feel it as a kind of gentle, invisible drag, a soft reluctance in your hand, as though the coil is quietly asking you to slow down. This opposition is not the universe being contrary for its own sake. It is simply the price of admission, the toll paid for turning motion into electricity. Every joule of electrical energy that appears in that coil had to come from somewhere, and Lenz's law is really just the universe's bookkeeping, insisting that the somewhere is you, the one pushing or pulling the magnet, doing a little more work than you would have if no current were being generated at all. Once you understand this dance between motion, changing flux, and opposing current, an enormous swath of the modern electrical world opens up, because a generator is really nothing more than an engineered, deliberate way of exploiting exactly this effect, over and over, thousands of times a second.
Instead of a hand pushing a magnet toward a coil, imagine a turbine spun by falling water at a dam, or by steam pressure in a power plant, or by wind turning great blades on a hillside, and that turbine's spinning shaft is connected to either a magnet or a coil, arranged so that as it rotates, the flux through a stationary set of wires constantly rises and falls, in a smooth, rhythmic, endlessly repeating cycle. Every one of those cycles produces its own little pulse of induced voltage, and strung together thousands of times each second, these pulses become the alternating current that flows quietly through the walls of the room you may be lying in right now, indifferent to whether you are awake to notice it. The same underlying principle, slightly rearranged, gives you the transformer, that unglamorous metal box you might have seen humming on a utility pole or sitting heavy and warm inside a phone charger. A transformer takes two separate coils of wire wound around the same shared iron core without the wires themselves ever touching.
Send alternating current through the first coil, and because it is alternating, constantly reversing direction, it creates a magnetic field that is also constantly changing, rising and falling, and reversing in step with the current. That changing field travels through the shared iron core exactly the way the field from an electromagnet's coil traveled through its core earlier, and when it reaches the second coil, sitting there passively, with no wire connecting it to anything, that changing flux induces a voltage in it too, entirely through empty space and shared iron, without a single electron ever crossing over from one coil to the other. Depending on how many times each coil is wound around the core, the voltage can be stepped up or stepped down between the two sides, which is precisely how electricity generated at a power plant gets boosted to enormous voltages for efficient travel over long transmission lines, and then quietly stepped back down, transformer by transformer, until it arrives at your wall outlet at a voltage gentle enough to charge a phone. And there is one more everyday appliance worth mentioning here, sitting perhaps in a kitchen not so far from wherever you are now, that runs on this same quiet principle of opposition. An induction cooktop contains a coil beneath its glass surface, carrying a rapidly alternating current, and when a pot made of the right kind of metal is placed on top, the cooktop's changing magnetic field reaches up into the metal itself and induces small looping currents directly inside the base of the pot. Those currents meet resistance as they twist through the metal, and that resistance produces heat, real and immediate, without the cooktop's surface itself ever having to glow or burn at all. Let's slow down for a moment and think about something that has been quietly waiting in the background of everything we have covered so far. All this time, we have been talking about magnetic fields as if their only job were to induce things, to nudge electrons into motion inside a wire, to whisper energy from one coil to another across empty space. But magnetic fields do something else too, something more direct and more physical, and it is this other talent that turns motors and speakers and the muffled click of a relay into the ordinary miracles they are. Picture a single charged particle drifting through a magnetic field. If it sits still, the field mostly ignores it. But the moment that charge starts moving, something curious happens. The field reaches out and pushes on it, not in the direction the charge is traveling, and not in the direction the field itself points, but in a direction that is perpendicular to both at once. It is a strange kind of push, sideways to everything, like a river current that shoves a swimmer not downstream and not toward the bank, but somehow both away from the bank and along some third direction entirely. Physicists worked this out slowly, piece by piece, through the 1800s, and eventually it became known as the Lorentz force, named for the Dutch physicist Hendrik Lorentz, who helped formalize the mathematics late in that century, though the underlying pattern had been glimpsed by others before him. Now, a wire-carrying current is really just a long, orderly procession of moving charges, electrons filing along, one after another. So if you take that wire and place it inside a magnetic field, every one of those moving electrons feels that same sideways push. And because the electrons are confined inside the wire, unable to simply drift off on their own, that push transfers to the wire itself. The whole wire feels a force, perpendicular to both the direction the current is flowing and the direction the magnetic field is pointing. This is worth sitting with for a moment, because it is easy to let it slide past as just another rule, when really it is the reason your electric toothbrush hums, the reason your car door locks click shut, the reason the fan across the room is spinning it all. Think about how strange this actually is, if you imagine it slowly. A wire, minding its own business, carrying a modest trickle of electrons. It is not touching a magnet. It is not being pulled by any string. And yet, simply because it sits inside a magnetic field, while current flows through it, it feels a shove, real enough to move a needle, real enough to spin a rotor, real enough to press a speaker cone forward and pull it back thousands of times a second to shape the sound of a voice or a cello. Let's build this up, piece by piece, the way engineers eventually did, starting with the electric motor, since that is probably the single device most responsible for turning this strange sideways force into something civilization now runs on. Inside a simple motor, there is a loop of wire, free to rotate, sitting inside the field of a fixed magnet, usually curved to wrap around the loop on either side. Send current through the loop, and the two sides of it, moving in opposite directions relative to each other, because it is a loop, feel forces in opposite directions too. One side gets pushed up, the other gets pushed down, or however the geometry happens to work out, and the result is that the whole loop begins to twist, to rotate around its axis, driven by nothing more than this Lorentz force acting on opposite sides of the loop simultaneously. There's an elegant complication here that took real cleverness to solve. If the current just kept flowing the same direction as the loop rotated, the loop would twist halfway around, and then, having reached the point where the force would now push it backward, it would simply stop, or worse, reverse. Early motor builders solved this with a small mechanical trick called a commutator, a split ring that reverses the direction of current through the loop at exactly the moment it needs reversing, every half turn, so the twisting force keeps pushing the loop the same rotational direction over and over. It is a bit like pedaling a bicycle and knowing, without thinking about it, exactly when to apply pressure to keep the wheel spinning smoothly rather than stalling at the top of each stroke. Modern motors have refined this idea in dozens of ways, some using multiple coils, some using electronics instead of mechanical contacts to manage the switching, but the essential trick, timed reversal, to keep the push going the right direction, remains at the heart of nearly all of them. This same sideways force,
once you know to look for it, turns up in places that seem to have nothing to do with spinning wheels at all. Consider the loudspeaker sitting somewhere in your home, perhaps built into a phone or a set of headphones resting nearby right now. Inside it, a small coil of wire, called the voice coil, sits wrapped around a cylindrical gap in a stationary magnet attached to a lightweight cone. When an audio signal, which is really just a rapidly varying electric current, flows through that coil, the coil feels a force from the surrounding magnetic field. And because the current is constantly changing in strength and direction, following the shape of whatever sound is being reproduced, the force on the coil changes too, pushing the cone forward, pulling it back, forward and back, thousands of times each second, each tiny motion nudging the air just enough to recreate the pattern of a violin string or someone's voice. The whole apparatus of recorded music, in some sense, comes down to this: a wire, a magnet, and the sideways push between them, oscillating fast enough that your ear reads it as sound rather than as separate little taps. There is something worth noticing in how symmetrical all of this is with what we discussed earlier. A changing magnetic field can induce current in a wire, and now we're seeing that current in a wire moving through a magnetic field produces motion. These are, in a real sense, two faces of the same underlying relationship, one running forward and one running in reverse. A speaker converts electrical current into motion. A microphone, built almost identically, with a coil attached to a diaphragm instead of a cone, does the opposite, converting the motion of sound waves into a small induced current. Spin a motor by hand instead of powering it electrically, and it will generate a small voltage of its own, briefly becoming a generator instead of a motor. The same coil, the same magnet, doing opposite jobs depending on which end you started from.
Hard drives, at least the older mechanical kind with spinning platters, use this same force in miniature, precisely, to steer a tiny read and write head back and forth across the surface of a spinning disk, with astonishing accuracy, guided by coils and magnets working together in what is essentially a very small, very fast, very carefully controlled motor, and relays, those unassuming little components that click audibly inside appliances, use it in an even simpler form. A relay is really just an electromagnet positioned near a small metal lever. Send current through the coil, the resulting magnetic field pulls the lever, and the lever's motion closes or opens a separate electrical connection somewhere else entirely, letting a small, safe current in one circuit control a much larger current in another. That soft click you sometimes hear inside an old thermostat or a washing machine right before something switches on is often exactly this: a magnetic pull yanking a small metal arm across a small gap. So many of the tactile sensations woven through a day, the satisfying resistance of a laptop lid held shut by a hidden magnet, the muted thump of a speaker cone, the quiet spin of a fan motor cooling a room, all trace back to this same underlying idea, a moving charge feeling a sideways push from a field it happens to be traveling through. It is worth letting that settle for a while, this notion that pushing and pulling in so much of modern life is not really about magnets touching things directly at all, but about charges in motion, feeling a force from a distance, in a direction neither they
nor the field itself are pointing. There is still more to uncover here, particularly around what happens when we look closer at the shape of that push, and how its strange perpendicular nature connects to something even more fundamental about how electricity and magnetism relate to each other in the first place.
Let's set all of that aside for a while, the coils and the relays and the soft mechanical clicking, and go somewhere smaller, somewhere stranger. Because underneath every magnet you have ever held, every refrigerator magnet shaped like a tiny fruit, every compass needle trembling toward north, there is a question that took physics a remarkably long time to answer properly. Where does the magnetism actually come from? Not the electromagnet, with its obvious coil of wire and its obvious battery. The other kind, the permanent magnet, the plain gray bar of metal that does nothing, draws no current, has no wires attached to it, and yet reaches out into the space around it and pulls a paperclip across a table. It is worth sitting with how strange that is, if you let yourself really notice it. A battery-powered magnet makes sense in the way a fan makes sense. Energy goes in, motion comes out, and if you unplug it, the motion stops. But a bar magnet on your desk is not plugged into anything. It has been sitting there, pulling on nearby iron, for months, maybe years, without ever running down, without ever needing to be recharged, without a battery hidden inside it, doing quiet, invisible work. And this used to bother people, reasonably, because it looks so much like a machine that runs forever for free, which is exactly the kind of thing nature tends not to allow. So let's go find out what is really happening in there, gently, the way you might approach any small mystery late at night, without needing to rush toward the answer. The first clue came from William Gilbert, the physician to Queen Elizabeth I, who in the year 1600 wrote a book called De Magnete, and correctly guessed, remarkably, that the Earth itself was a giant magnet, long before anyone understood why. But Gilbert could only describe what magnets did. The why had to wait more than 3 centuries, and it had to wait specifically for the discovery of the electron, and then for something even smaller and stranger sitting inside the electron, something physicists eventually named spin. Spin is one of those words that physics borrowed from everyday life and then quietly hollowed out and refilled with something almost unrecognizable, so it deserves a careful, slow introduction, the kind you can hold loosely rather than gripping too tightly. When you hear the word spin, you probably picture a top twirling on a table, or a planet turning on its axis, a small object physically rotating in space. And in the early days, physicists reached for exactly that picture, imagining the electron as a tiny charged ball, literally spinning like a miniature planet, and that spinning charge, they reasoned, would create its own little magnetic field, the same way a loop of current does, only far, far smaller. It is a lovely image. It is also, as best anyone can tell, not literally true, and this is one of those places worth pausing on and labeling clearly as a simplification rather than letting it slide by, disguised as fact. As far as every experiment has ever shown, the electron has no measurable size at all. It behaves, in every test physicists have devised, like a point, with no surface that could be spinning, no little equator, nothing physically rotating in the ordinary sense of the word. And yet it still carries something that behaves exactly like a spinning charge would, a tiny built-in magnetic personality, present from the moment the electron exists, needing no motion, no history, no cause. It is not spinning the way a top spins. It simply has spin, as an intrinsic property, the way it has charge, or mass,
You do not ask why an electron has charge, it just does, as part of what it means to be an electron. Spin turns out to be the same sort of thing, and the twirling ball picture is best kept as a comfortable analogy, useful for building intuition, not as a literal description of tiny billiard balls pirouetting inside atoms.
So here is the first real ingredient of magnetism at its root. Every electron in the universe behaves as though it is an impossibly small bar magnet, permanently, all on its own, whether or not it is moving anywhere, whether or not it is part of a current, whether or not it is orbiting anything at all. But electrons are not only spinning, in this borrowed, careful sense of the word, inside an atom, they are also in motion around the nucleus, in the fuzzy, cloud-like way quantum mechanics describes, rather than the neat little orbits Bohr once drew. And a moving charge, as the earlier sections of this walk through magnetism kept returning to, again and again, creates a magnetic field. So each electron in an atom contributes two separate magnetic effects, layered on top of each other. There is the magnetism from its spin, which it carries simply by existing, and there is a second contribution from its orbital motion around the nucleus, which behaves, in a rough and useful analogy, like an impossibly tiny loop of current circling a tiny wire, exactly like the electromagnet coils from earlier sections, only shrunk down to the scale of a single atom. Now, if every electron is its own small magnet in two different ways, you might reasonably expect every single atom, and every material made of them, to be strongly magnetic. Wood should stick to a fridge. Skin should stick to a fridge. And obviously, it doesn't, which means something else must be happening to cancel most of this out, most of the time, in most materials. That something else has a name borrowed from bureaucracy and paperwork, oddly enough. It is called the Pauli exclusion principle, after the Austrian physicist Wolfgang Pauli, who proposed it in 1925 while trying to make sense of the patterns in the periodic table. The principle, stated plainly, says that no two electrons in the same atom can occupy exactly the same quantum state at exactly the same time, and one of the consequences of this rule is that electrons tend to pair up inside atoms, two to a slot, with their spins pointing in opposite directions, one up, one down, in the rough language physicists use for this. When that happens, their tiny magnetic effects, being opposite, cancel each other out almost perfectly, like two people pulling a rope with equal strength in opposite directions, producing no net motion at all. This is why most ordinary materials are not magnetic in any noticeable way. Their electrons are almost entirely paired off, spin up against spin down, each pair silencing itself internally, leaving no net magnetism to speak of on the outside. It is a strange kind of peace, achieved by design, or rather achieved by a rule so fundamental that the universe simply does not permit the alternative. But a small number of elements, iron chief among them, along with nickel and cobalt, have an unusual arrangement in their outer electrons, leaving some of them unpaired, spinning, in that borrowed sense, without a partner to cancel them out. Each of these atoms, then, behaves like a tiny leftover bar magnet of its own, faint but real. And in most materials, even with unpaired electrons present, these tiny atomic magnets point every which way, jumbled and random, the way a room full of compass needles might point if you shook the room hard enough, and their effects wash out across the material as a whole, canceling by sheer disorder rather than by pairing. Iron is different, and this is where the true answer to the battery question finally starts to come into view. In iron, and in a handful of other materials, there is an additional quantum effect
called the exchange interaction, which, rather than canceling neighboring atomic magnets, encourages them to line up, to point the same direction as their neighbors, the way a rumor might spread through a small town until nearly everyone is facing the same way, nodding along together. This is not a force pulling them into alignment, the way two bar magnets pull each other. It is subtler and stranger than that, rooted in the Pauli principle again, in how electrons from neighboring atoms are willing, energetically, to arrange themselves relative to each other. But the outcome is what matters here for now. Enormous numbers of atomic magnets, across a chunk of iron, end up nudged into pointing the same direction as their neighbors, reinforcing rather than canceling. And that is the answer, finally, to the mystery of the desk magnet with no battery. Its pull is not powered by anything running down, because nothing is running at all, in the sense of consuming energy over time. It is powered by alignment, by a vast number of electrons that were always going to behave like tiny magnets, simply by existing, now cooperating instead of canceling, all quietly facing the same direction, the way a stadium of fans might already be seated, needing no ongoing effort at all, to keep pointing toward the field. The magnet does not spend energy to keep pulling. It costs nothing to stay aligned, the same way it costs nothing for a book to stay closed once it has been shut. There will be more to say, gently, about how that alignment can be broken, and what happens to a magnet when it gets too hot to hold its formation together.
Let's turn now from the small alignment of electrons to something almost too large to picture, and yet, in a way, it works by a similar principle. The whole earth beneath you, right now, as you lie there, is behaving like a magnet, and it has been doing so for something like 3.5 billion years, quietly, patiently, long before there was anyone around to notice or to name it. Here is a strange fact to sit with for a moment. The magnetic north that a compass needle points toward is not the same as the geographic North Pole, the fixed point at the top of the globe where all the lines of longitude converge. They are close, relatively speaking, but they are not the same place, and they have never been the same place, not exactly. The geographic pole is defined by the planet's spin, by the axis Earth turns on as it rotates through one day and one night. The magnetic pole is defined by something else entirely, something churning deep underground, and it wanders. Slowly, but it wanders. If you had a very good compass and a lot of patience, and you tracked the magnetic pole over the course of your life, you would find it had crept a noticeable distance from where it was when you were born. In recent decades, it has been moving with unusual speed, drifting from northern Canada out across the Arctic toward Siberia, at a pace that has sometimes startled the scientists whose job it is to keep track of such things. So where does this wandering magnetism actually come from? The honest answer took a very long time to arrive at, and it did not come easily. For centuries, people simply used the compass without asking too deeply why it worked, which is a very human thing to do, to use a tool faithfully while treating its inner workings as a kind of pleasant mystery. Sailors trusted the needle because it had earned their trust, voyage after voyage, without needing to explain itself. It was the English scientist William Gilbert, working at the end of the 1500s, who first proposed, carefully, using a small magnetized sphere he called a terrella, a little earth, that the planet itself might be one enormous magnet. He rolled a compass needle over the surface of his little iron ball and watched it behave exactly as compasses behaved on the real Earth, dipping and turning
in matching ways, and from that simple, patient experiment, he drew a genuinely bold conclusion for his time, that the whole world beneath our feet was itself magnetized. Gilbert was right about the effect, though he had no way of knowing the cause, because the cause lies thousands of kilometers beneath the surface, in a place no one has ever visited and no one ever will, given the heat and the pressure involved. Beneath Earth's crust, beneath the thick, slow-moving mantle, there is a core made mostly of iron and nickel, and this core has two distinct layers. The inner core is solid, packed under such extraordinary pressure that the iron there stays solid even at temperatures hotter than the surface of the sun. Surrounding that solid inner core is the outer core, and this part is liquid, a vast ocean of molten metal, swirling and churning in slow, powerful currents, driven by heat, escaping from the inner core and by the planet's own rotation. This churning liquid metal is where the magnetism is actually made, through a process called the geodynamo, and it is worth taking a moment to picture what that word is describing, because it is not a static object sitting down there generating a field the way a bar magnet does. It is a process, an ongoing, self-sustaining motion. Molten iron is an excellent conductor of electricity, and as it flows and swirls, carried along by heat rising from the core and twisted by the Coriolis effect from Earth's spin, those moving currents of charged material generate electric currents, and electric currents, as you may remember from earlier in this journey, generate magnetic fields of their own. And here is the elegant, almost circular part. The magnetic field, generated by that motion, then acts back on the moving liquid metal itself, reinforcing certain patterns of flow over others, so the whole system becomes self-sustaining, a feedback loop that has kept itself running for billions of years without any outside push, the way a spinning top, once given its initial motion, can keep itself upright for a surprisingly long time through nothing but its own steady momentum. Because this generator is powered by turbulent, chaotic fluid motion, it is not perfectly steady, and this is part of why the magnetic pole wanders the way it does instead of sitting in one obedient spot the way the geographic pole does. The pattern of flow down there shifts and drifts, and the surface expression of that flow, the place where field lines cluster most tightly, shifts and drifts along with it. It is a little like watching smoke rise from a candle in a still room. For a while, the smoke rises in a fairly steady column, and then some small internal turbulence sends it curling off in a new direction, not because anything outside the room changed, but because the motion itself was never perfectly smooth to begin with. Now, there is something else the outer core has done throughout Earth's history that tends to alarm people more than it probably should, and it deserves a calm, unhurried look. From time to time, over the vast span of geological time, Earth's magnetic field has flipped entirely, with the north and south magnetic poles trading places. Scientists know this happened because of a remarkable natural record preserved in rock.
When molten rock rises up through the mid-ocean ridges and cools, tiny magnetic minerals within it lock into alignment with whatever the magnetic field happened to be at that exact moment, like a compass needle frozen mid-swing, and then that alignment stays fixed in the rock forever after, a little fossil of the field as it once was. Reading these frozen alignments, in rock after rock, layer after layer, geologists found stripes of alternating polarity marching outward from the ridges in a symmetrical pattern, and from this they were able to piece together a timeline of reversals stretching back tens of millions of years, sometimes hundreds of millions. These reversals happen irregularly, and they are not sudden events on a human timescale. A full reversal seems to unfold over a period of somewhere between 1,000 and 10,000 years, which sounds sudden if you compare it to the billions of years of Earth's whole history, but is achingly slow compared to a single human life, let alone a single news cycle. During the transition, the field does not simply vanish or shut off entirely, and it does not stay a clean, simple pattern either. It seems to grow messier, weaker in places, developing multiple patches and false poles before eventually settling into its new, reversed configuration. It is worth saying plainly that despite what you may have encountered in more sensational corners of the internet, there is no credible scientific evidence that a pole reversal would strip away the atmosphere, cook the surface, or end civilization. Life on Earth has weathered many hundreds of these reversals across the planet's history, and the fossil record shows no matching pattern of mass extinction lining up with them. It is a real and fascinating process, but it is not the apocalyptic one it sometimes gets dressed up as. What the magnetic field does do, reliably, whether it is stable or slowly reversing, is help shield the planet from something arriving constantly from beyond it. A steady outward breath from the sun, called the solar wind, a thin stream of charged particles, mostly protons and electrons, blown outward from the sun's scorching upper atmosphere in every direction, including straight toward us. Without any kind of shielding, this wind would slowly strip away the lighter parts of Earth's atmosphere over geological time, the way a steady breeze can slowly wear grains of sand from the top of a dune. But Earth's magnetic field reaches far out into space, forming an invisible, teardrop-shaped bubble around the whole planet called the magnetosphere, blunt and rounded on the side facing the sun, stretched long into a tail on the side facing away, like the wake trailing behind a boat moving through water. Most of the solar wind is deflected around this bubble entirely, the charged particles curving around Earth the way a river current curves around a rock, never touching us at all. Not all of it is deflected so cleanly, though, and this is where the sky itself joins the story. Near the magnetic poles, where the field lines dip down and funnel into the planet rather than curving safely around it, some of those charged particles from the solar wind are guided down into the upper atmosphere, and there they collide with oxygen and nitrogen atoms, and this is what produces the shimmering curtains of the aurora, borealis in the north, australis in the south, colors of green and red and sometimes violet spilling silently across the night sky in places far enough north or south to catch them. It is a strange and lovely thought to hold on to as you drift off, that the same invisible field, bending your compass needle in some quiet room, is also, at this very moment, painting light across the sky somewhere much colder and much darker. Let's turn now from the very large to the very ordinary, from a planet-sized bubble of protection down to something you could hold in your hand, because it turns out that almost everything around you, right now, in whatever room you are lying in, is responding to magnetism in some small way, even if it never occurred to you to wonder about it. Start with iron, since iron is the material most people picture when they hear the word magnet at all. A nail, a paperclip, the frame of an old iron gate left out in the rain. These are ferromagnetic materials, and the name simply means iron-like. from the Latin ferrum, though the family includes cobalt and nickel, and a handful of others besides. What makes them special is something we touched on earlier and can now look at a little more closely, almost drowsily, the way you might turn a smooth stone over in your palm. Inside a piece of iron, the electrons are arranged so that huge numbers of neighboring atoms want to point their tiny magnetic moments in the same direction as each other, not because anyone told them to, but because it costs them less energy to align than to disagree. It's a bit like a crowd of people humming the same note in a large stone room. No single voice is doing anything remarkable, but the tendency to match your neighbor spreads outward until whole sections of the room are humming together in one great low chord. In unmagnetized iron, these humming sections, called domains, point in many different directions, canceling each other out, so the nail on your workbench shows no overall pull. But drag a strong magnet along that nail a few times, and you nudge the domains into agreement, more of them humming the same note, until the whole nail itself becomes a weak magnet, able to pick up a second nail and even a third. Ferromagnetism is the dramatic case, the one that can lift a car in a scrapyard or hold a note to a refrigerator door for years without tiring. But step down in intensity and you find paramagnetism, a much gentler cousin. Paramagnetic materials, things like aluminum, platinum, and liquid oxygen, do have atoms with their own small magnetic moments, tiny compass needles at the atomic scale, but unlike iron's atoms, these needles don't care much what their neighbors are doing. Left alone, they point every which way, jostled constantly by ordinary thermal motion, the same restless jiggling that makes a pot of water simmer before it boils. Bring a strong magnet nearby, though, and something subtle happens. The atomic needles begin, weakly and reluctantly, to tilt in the direction of the applied field, the way a room full of people idly facing random directions might, ever so slightly, turn their heads if someone near the doorway called out a name. The moment the outside magnet is removed, the alignment collapses back into randomness almost instantly, the atoms returning to their own private business. This is why you cannot make a permanent magnet out of aluminum, no matter how strong a magnet you rub it with. It will feel the faintest pull, while the other magnet is close, an attraction so weak it would never register on an ordinary kitchen scale, and then it simply lets go. Then there is diamagnetism, which is stranger still, and which almost nobody encounters as a bedtime thought, though it deserves to be one, because it means nearly everything, including you, is very faintly magnetic, in a way that pushes away from a magnet rather than toward it. Diamagnetism doesn't come from atoms with their own built-in magnetic needles at all. It comes from something more universal, a tiny electrical response that every material has, because a changing magnetic field, even one just being switched on, induces a small circulating current in a material's electrons, and by a rule discovered by the French physicist Jean-Baptiste Biot's contemporaries, and refined over the following century, that induced current always opposes the change that created it. The result is a whisper of repulsion, present in every material on Earth: water, wood, glass, human skin, even bone, but so faint that it is almost always drowned out by other, stronger magnetic effects, if any are present. Water is diamagnetic, which sounds like a strange thing to say about something that fills up a glass so uneventfully, but it's true, and it leads to one of the most delightfully odd experiments in modern physics. In the late 1990s,
At a high magnetic field laboratory in the Netherlands, researchers led by André Geim, who would later share a Nobel Prize for his work on graphene, placed a live frog inside an extremely powerful magnetic field, strong enough to reveal diamagnetism's usually invisible effect on the water inside living tissue. The frog floated, suspended gently in midair, inside the bore of the magnet, held up entirely by the faint repulsion of its own water content, pushing back against the field. The frog, by all accounts, seemed unbothered by the experience, and was returned safely to its terrarium afterward. It's a strange image to hold in your mind as you drift. A small green frog hovering in still air, weightless, not because gravity had been switched off, but because every drop of water in its body was quietly refusing an intruding magnetic field, the same reluctance you would feel too, if someone built a magnet large enough to test you. There's a fourth, quieter member of this family worth knowing about before we move further, called antiferromagnetism, and it might be the strangest of the group precisely because it produces almost nothing you could ever detect by touch. In certain materials, chromium among them, and manganese oxide as another well-studied example, neighboring atoms do align with their neighbors, just as they do in iron, but instead of pointing the same way, they alternate, one atom's needle pointing up, the very next pointing down, up, down, in a strict and orderly pattern that repeats through the whole crystal like the black and white squares of a chessboard. The overall effect, from the outside, is nothing at all. All those opposing needles cancel each other so completely that a block of antiferromagnetic material held in your hand would feel exactly as unmagnetic as a plain stone, even though internally it is arranged with just as much precision and cooperation as any magnet you've ever held, just organized towards silence instead of towards strength.
And then there is a final case that isn't really about atomic needles at all, but about electricity finding a way to erase a magnetic field completely, which is what happens inside a superconductor. We touched briefly, earlier in this drifting explanation, on how certain materials, cooled down close to absolute zero, lose all resistance to electric current, allowing currents to flow forever without fading. What we didn't quite finish saying is what those materials do to a magnetic field trying to enter them. In 1933, two German physicists, Walther Meissner and Robert Ochsenfeld, discovered that a superconductor doesn't simply resist a magnetic field the way a diamagnetic material weakly does. It expels the field almost entirely, pushing it out from its interior as it cools past its critical temperature, in an effect that now carries their names, the Meissner effect. Surface currents spring up automatically around the material's outer edge, currents that flow without any battery or wire, purely as a response to the intruding field, and those currents generate their own opposing field strong enough to cancel the original one everywhere inside. The practical result of this, and the part best suited to picturing right before sleep, is that a magnet brought close to a superconductor doesn't just feel a gentle push, the way the frog's water did. It can be made to float above it, cleanly, stably, hovering in open air with no visible support, a small stone of metal resting on nothing but its own reflection in a field it cannot enter. Physics demonstrations built around this effect often use a disk of the ceramic superconductor called yttrium barium copper oxide, cooled in a shallow bath of liquid nitrogen until it fogs gently with cold vapor, and a small magnet is then simply set above it and released, and it does not fall. It just sits there, quietly, an inch or two above the cold white cloud, as if gravity, in that one small space, had briefly forgotten its job. There's something almost soothing about a floating magnet that has never fallen since the demonstration first began, and it seems like a fitting place to turn toward the questions that haven't been answered yet. The loose threads physicists still turn over quietly, sometimes for decades, sometimes for a century or more. Start with the magnet itself, and the strange fact we mentioned only in passing, that every magnet ever found in nature or built in a laboratory has two poles, north and south, always together, always inseparable. Break a bar magnet in half, and you don't get an isolated north and an isolated south sitting apart on a table. You get two smaller magnets, each with its own north and south, as though the poles keep dividing themselves into new pairs no matter how far the breaking goes, all the way down, presumably, to the level of a single electron's spin. In 1931, the physicist Paul Dirac, working through the mathematics of quantum theory almost as a kind of idle curiosity, noticed something odd. If a single isolated magnetic pole, a monopole, ever existed anywhere in the universe, it would explain, elegantly and completely, why electric charge comes in the tidy discrete units it does, why there's a smallest possible chunk of charge and nothing in between. It was a beautiful piece of reasoning, the kind that makes physicists sit up a little straighter, and it has motivated searches ever since. Delicate detectors buried in mine shafts and cooled in cryostats, waiting for the one signature a monopole would leave behind. None has ever shown up. The Dirac monopole remains a permitted guest that hasn't come to the party, a solution allowed by the equations, consistent with everything else we know, and yet absent from every observation anyone has managed to make. It's the kind of gap that keeps a theory honest, a reminder that having consistent mathematics is not the same as having proof. While we're out at the edges of what's known, consider the magnetars, because it would be strange to spend this many hours drifting through magnetism without pausing at the strongest magnets that exist anywhere. A magnetar is the collapsed core of a massive star, a neutron star so dense that a teaspoon of it would outweigh a mountain, and in a small fraction of these collapsed cores, the magnetic field left over from the original star gets compressed and amplified to levels that don't have a comfortable human comparison. A strong medical scanner might produce a few Tesla. The surface field of a magnetar can reach numbers in the range of 10 to the power of 10 or 11 Tesla, a field so intense that, according to the physics, it would distort the shapes of atoms themselves, stretching their electron clouds into thin cigars aligned with the field rather than the fuzzy spheres they form on Earth. Nobody has taken an atom to a magnetar to check this directly, of course. The prediction rests on extending known physics into a regime so extreme that it becomes, in a sense, its own kind of question mark, a place where the theory is trusted mostly because it has worked everywhere, gentler, and it's left to quietly imply what must be happening in conditions no laboratory could ever survive. Astronomers detect magnetars indirectly through sudden bursts of X-rays and gamma rays, occasional starquakes, thought to occur when the crust of the star cracks under the strain of its own field, a small settling shudder happening trillions of miles away and read here on Earth as a flicker of high-energy light. Closer to ordinary temperatures, but no less puzzling, are the quantum materials that condensed matter physicists have spent the last several decades slowly mapping, materials whose magnetic behavior doesn't fit neatly into the ferromagnetic, paramagnetic, diamagnetic categories laid out earlier. There are spin glasses, in which magnetic moments freeze into a disordered tangle, pointing in directions that look almost random and yet aren't quite, like a room full of weather vanes, locked in place by a wind that blew unevenly and then simply stopped. There are spin liquids, a name that sounds like a contradiction and rather enjoys being one. Materials in which the magnetic moments refuse to settle into any fixed pattern, even as the temperature drops toward absolute zero, continuing to fluctuate and rearrange the way water molecules do in a liquid, except here, it's the tiny magnetic orientations doing the shifting, rather than the atoms themselves. These aren't yet fully understood, and researchers describe them, when pressed, with a certain honest hesitation, because the mathematics that works beautifully for a simple bar magnet starts to strain and complicate itself once millions of interacting quantum spins are involved, each one nudging its neighbors, each nudge changing the rules very slightly for the next. Then there's a question that sits closer to home, if home happens to include feathers or fur. Certain birds, sea turtles, and a handful of other animals appear able to sense the Earth's magnetic field and use it for navigation, a capacity called magnetoreception, and it remains one of the more contested puzzles in modern biology. The leading idea, still debated, involves a light-sensitive protein called cryptochrome, found in the retinas of birds such as European robins, in which absorbing light briefly creates a pair of electrons whose quantum spin states are sensitive to the surrounding magnetic field, in a way that might, the hypothesis goes, subtly alter the chemistry of vision itself, perhaps letting a migrating bird see the field as a faint overlay on its ordinary eyesight, a shadow, or a brightness laid across the sky, that has nothing to do with light. It's an elegant idea, and some careful experiments support it, showing that a robin's sense of direction can be disrupted by extremely weak radio frequency fields, too faint to do anything else detectable, exactly the kind of disruption a quantum spin effect would predict. But other researchers point to a second, quite different mechanism, tiny crystals of magnetite, an iron mineral found in small quantities in the beaks or other tissues of some migratory animals, which could in principle act as microscopic compass needles wired into the nervous system. Both mechanisms might be real, operating in different species, or even together in the same one, and the honest answer, if you asked a biologist studying this tonight, is that nobody has settled it completely. It's worth pausing, too, on something more mundane, which is why an ordinary refrigerator magnet gradually gives up its strength over the years, growing weaker in a way that has nothing to do with monopoles or magnetars. Heat is the main culprit, because raising a magnet's temperature gives its aligned atomic domains more thermal energy to jostle around with, gradually knocking some fraction of them out of alignment, even without reaching the full Curie point where alignment collapses altogether. Physical shocks do something similar on a smaller scale, a dropped magnet absorbing a jolt that nudges a few domains out of formation, the way a tidy row of compass needles might shuffle slightly if the table under them were struck. And opposing fields, even weak stray ones encountered over months or years, slowly chip away at the alignment too, a little erosion that never fully reverses, because a magnet doesn't heal from wear the way some materials heal from small deformations. It simply, slowly, remembers less well. And underneath essentially everything discussed across every one of these sections lies a piece of geometry, so basic it's easy to forget it needs explaining at all, which is why any field, magnetic, gravitational, or otherwise, gets weaker the farther away you stand from its source. Picture the field lines around a magnet as threads spreading outward in all directions from a small point, and imagine trying to count how many threads pass through a patch of wall held up close versus a patch of the same size held far away. Close up, the threads are still bunched tightly, most of them still passing through your small patch of wall.
Farther out, those same threads have spread across a much larger area, a sphere expanding outward, whose surface grows with the square of the distance. So the same fixed number of threads gets shared out over more and more space, thinning as it goes, which is why the field so often falls off with the square of the distance, rather than fading in a straight, even line. It's not magnetism behaving mysteriously. It's simple geometry, the unavoidable consequence of anything spreading outward in 3 dimensions from a single source. And it happens to gravity, to light, to sound, to nearly every influence physics knows how to describe.
Let the room settle again, the way it has been settling all along, and let your attention drift back to whatever ordinary things are near you, because everything explained tonight lives quietly inside them. The metal frame of the bed, a coin on the nightstand, the small motor humming somewhere in the refrigerator down the hall. None of it looks magnetic, and most of it isn't, not in any way you could test with a fridge magnet, but all of it is built from atoms, and every one of those atoms is doing the same quiet thing that started this whole story so many sections ago. Electrons circling, spinning, behaving less like tiny orbiting planets and more like small persistent loops of current, each one a faint magnet in its own right, far too faint to notice alone. In most materials, those tiny magnets point every which way, canceling each other out the way a crowd of people all shouting different words produces only noise, no message. But in certain materials, iron chief among them, something changes. Groups of atoms fall into step with their neighbors, not because anyone organizes them, but because it costs them less energy to align than to fight each other. The same quiet logic that makes a stretched rubber sheet settle into its lowest, calmest shape rather than staying wrinkled. Those aligned patches are the domains, small regions, where a great many atomic magnets already agree with one another, though the domains themselves usually still point in different directions from one patch to the next, like a field of tiny flags, all raised but blowing toward different corners of the yard. A piece of ordinary iron can sit there, full of these little aligned neighborhoods, and still show no overall magnetism at all, because the patches cancel each other the same way the individual atoms once did. Magnetize that iron, and nothing new is created. Nothing is added. The domains that already agreed with the direction of an applied field simply grow, nudging their neighbors to swing into line, the boundaries between patches shifting the way a crowd at a concert might slowly turn to face a new voice calling from one side. Enough domains align, and the iron itself becomes a magnet, its threads of influence now reaching out beyond its own surface, closing into loops that curve from one end back around to the other, because a magnetic field, unlike so many other things in physics, never seems to have loose ends. Every line that leaves eventually returns. Cut a magnet in half hoping to isolate one end from the other, and you don't get a lone north or a lone south. You get 2 smaller magnets, each with both, the pattern rebuilding itself at every scale down to the atom, which is one of the more genuinely strange things about this whole subject, and still not fully explained by anything simpler than the mathematics itself. Currents make this same kind of field without any iron at all. A wire carrying moving charge surrounds itself with circling magnetic influence, the same way that spinning electron does, just built from motion at a larger, more human scale, the scale of a coil of copper wire, something you could hold in your hand. Loop that wire enough times, and the field lines from each turn add together down the center of the coil, producing something that behaves, from the outside, almost exactly like a bar magnet, except this one can be switched on and off with nothing more than a switch,
because the moment the current stops, the moving charges stop, and the field that only ever existed because of that motion simply isn't there anymore. That's the heart of the electromagnet, the thing that lifts scrapped cars in a junkyard and rings a doorbell and, at a gentler scale, hums quietly enough to run the small motor in a fan. And the relationship runs both directions, which is perhaps the most quietly useful fact in this entire subject. A changing magnetic field, one that grows or shrinks, or simply moves past a piece of wire, pushes charges through that wire on its own, without any battery, without anyone applying voltage from outside. This is induction, discovered by Michael Faraday in a series of unglamorous patient experiments in a basement laboratory in London in 1831, where he wound coils of wire around iron rings and moved magnets by hand, watching a needle twitch on a meter whenever something in the arrangement changed. Not when the magnet sat still nearby, only when it moved, or when a nearby circuit switched on or off. That distinction, motion, or change over stillness, sits at the center of nearly every generator on Earth. The wire coil spinning inside a fixed magnetic field, or the magnet spinning inside a fixed coil. The same idea either way, converting the physical motion of a spinning turbine into the electrical current that fills the wires running through the walls around you right now, however far away that particular turbine actually is. Zoom in as far as physics currently allows, and magnetism doesn't come from tiny spinning balls of charge, the way an old classroom model might suggest, however useful that picture has been for keeping all of this straight in the dark. It comes from something called spin, a property every electron carries, that behaves mathematically like rotation, and produces a magnetic effect like rotation, but isn't quite rotation in the way a top or a planet rotates, because an electron isn't understood to be a tiny ball with a surface that could physically spin. It's simply a property the particle has, built into it the way charge and mass are built into it, discovered not by looking closer with a better microscope, but by noticing, in the 1920s, that electrons in atoms needed one more quiet property to explain patterns in how light interacted with matter, patterns that otherwise refused to add up. Physicists Samuel Goudsmit and George Uhlenbeck proposed the idea as graduate students in Leiden, somewhat nervously, since the numbers required something moving faster than light if taken too literally, and it worked well enough regardless, that spin has stayed in the description of the electron ever since. One of those cases where a name borrowed from everyday motion outlived any comfortable claim that the motion was literal. And zoom back out, all the way out, past the walls of the room and past the town, and past the curve of the horizon, and the same basic story turns up at planetary scale. Deep in the earth, past the solid crust and mantle, lies a core of liquid iron and nickel, churning slowly under heat left over from the planet's formation, and from the slow decay of radioactive elements within it, and that churning moves electrically conductive fluid in patterns that, much like Faraday's moving wires, generate electric currents, and those currents generate the planet's magnetic field, a process that sustains itself once started, called a dynamo.
It's the same principle as the wire coil in a generator, only built from a slowly stirring iron ocean thousands of kilometers below your feet, rather than a spool of copper you could hold in your palm. That field reaches out past the atmosphere, out into space, deflecting much of the charged particle stream, constantly arriving from the sun, the solar wind, the way a river splits gently around a stone, rather than punching straight through it. Without that deflection, the atmosphere itself would likely have thinned dramatically over geological time, stripped away particle by particle, the way it's thought to have happened on Mars once its own internal dynamo faded. So the compass needle from the very first section of this narration, the one that quietly points north on a windowsill or a nightstand, is doing something with a genuinely planetary cause,
aligning itself with a field generated by molten metal, turning far beneath the ground, a field that also happens to make the northern sky glow on the right night, and happens to keep the sky itself from slowly leaving. None of it needs remembering right now. The domains will keep aligning or drifting, whether you think about them or not. The currents will keep looping. The compass will keep finding north long after your eyes have closed, and the field above you will keep doing its slow, invisible work, exactly as it has, for longer than there have been eyes to notice it at all. Let all of it settle into the background now, the way it always was, quietly, without needing anything more from you. Rest well.